ABC Calc, this is going to be your day 19 notes. We're going to do a quick recap of linearization and differentials. So again, now's probably a good time to almost hit pause right away. Try and get a diagram that looks similar to this in your notes here, and then I'm just going to kind of walk through a quick description of what's going on here. It's pretty similar to the example that was in our day 18 notes with differentials, just kind of illustrating that if you have the slope of the tangent line at this point P right here, that corresponds with x sub 0, that we can use the slope of the tangent line, this dy right here, to estimate the actual change in y to the function. And as a quick note, we talked about this a little bit yesterday, that the error there would increase the further you get away. So if I change my delta x, to be even more, that tangent line at point P, it's really going to have more error in this region here than if I have my delta x to be pretty small. We're going to get less error there. Okay, so just going to describe a few things. I don't think we used epsilon at all yesterday, but if you look down below here, we have that delta y over delta x. Okay, the slope of the secant would be equal to the slope of the tangent plus a little bit of error. So that little error there we can define as epsilon, and then multiplying through by delta x would get you that the change in y is equal to, dy dx delta x plus this little error piece right here, which now is defined as epsilon delta x. To get the new y value, we talked about these yesterday, it's f of x sub 0. It's the function value at x sub 0 plus our delta y, where delta y is approximately equal to f prime of x dx. Okay. Similarly with linearization, we can find the new y value by doing f of a plus delta y. So we can approximate our delta y in this case to be f prime of a delta x, and the change in x when we're doing linearization is the difference of x minus a. So it's really the same exact concept, just maybe different ways of approaching it notationally. And as a quick reminder, the exam questions might ask you to use one method as opposed to another. So just make sure you feel comfortable and confident using both techniques, slightly different notations. Okay, L of x really just gives you the actual equation of the tangent line, whereas when we're dealing with differentials, we usually don't write the full out equation of the tangent, but we use the slope of the tangent at our given value of x to help approximate that new y value. Okay. All right, so if we're good just with that, a lot of notation here. So you'll check in with me when I see you next to let me know if you have questions about this. But why don't you go ahead and use differentials on the next page to approximate the cube root of 26. And this is really close to a value that we're familiar with and comfortable with, right? We know a cube root that's pretty close by to 26. So think about what function f of x you want to define here. Think about at what x value you would be finding the slope of that tangent. And then think about what your delta x is in that case based on what you've defined. See if you can use differentials to approximate the cube root of 26. Check it on the calc when you're done. See how close the approximation winds up being. All right, I'm giving you a lot to do on your own today because on the next page, I feel like this will go pretty quickly for you. Should take, I would say, under a minute to match the 4 graphs that are on the top half of the page, 1, 2, 3, 4, with the green derivatives below it. Yours probably are not green based on your copy, but you have them labeled as A, B, C, and D. So take these graphs, which represent the derivatives of the functions above, and see if you can do some really quick matching there. When we come back and go over this tomorrow, I'll be asking you to explain why you chose your specific pairings there. What were you looking at? What were you looking for? How did you make some of those decisions? All right, on the next 2 pages, it's just kind of a lot of reading. The definitions that we'll see at the top of this page as they deal with local and absolute max and mins can be found on page 260. In fact, these images were actually just snapshots that I took from your textbook. So you can quickly refer to them there if needed. But it's just kind of illustrating a little bit about local and absolute extrema. So you can see that in this diagram, we have a local max. Okay, it says there's no greater value of f nearby. So over a certain period of time, that's the highest point locally in this section of the graph. Here's a local min. Here's another local min at the endpoint of the interval from A to B. But since this is a closed interval, we can also define an absolute min. The absolute lowest point on this graph from A to B is at x equals A. And then over here, we have an absolute max point. And then the absolute max is located at x equals D. So graphically and visually, hopefully that makes sense. The actual definitions of local and absolute extrema are given right below. So again, if you have any questions there, that's definitely found on page 260 in your book. So what we want to talk about is then, how do I use calculus to be able to determine where some of these things are? Because we know we can type a function y equals on the calculator and be able to determine extrema pretty easily by calculating maxes and mins. But hopefully after looking at this graph in particular, you can see, you know what, there's definitely going to be a way using some calculus techniques to get those horizontal tangents that we're seeing drawn there to these specific points on the curve. Okay, so we're going to see that in just a second here. Let's talk about what the first derivative tells us. It tells us a lot of things, actually. One of them is we can tell where a graph is increasing and decreasing. So if you read the definition, if f is continuous at each point of this closed interval and differentiable at each point on the interior. So you can't be differentiable at an endpoint, but at any point on the open interval, if it's continuous and differentiable, if f prime is greater than 0 at each point on this interval, then f increases over that closed interval A to B. But meanwhile, if f prime, the slope of the tangent line, is negative, less than 0, then we know that the original graph f is decreasing over that interval. And that, I hope, makes sense to you, but if not, the visual below really does a nice job showing that. And then the first derivative theorem for local extreme values, if a function has a local max or local min at an interior point C of its domain, and f prime exists at C, then f prime of C must be 0. And that's what I was kind of referencing on that last page when I was talking about, hey, look at these horizontal tangent lines. Horizontal tangents should be screaming out to you, slope of the tangent is equal to 0. So that's what we're saying, is that over a certain interval, a function would exhibit local maxes and mins if the derivative at those values is equal to 0. So this picture is a really nice illustration of that. You can see that any of our tangent lines between point A and C, if you were to draw them to the curve, would all have positive slopes. So that's what all those positives mean down here. So when the derivative is greater than 0, we know that the original function is increasing. Then we get up to this point up here. The slope of the tangent line is 0, and it happens to be a local maximum point. So what we're going to find is when the function changes from increasing to decreasing, meaning that the slopes are changing from positive over to negative, that's where we'll know the graph exhibits a local maximum. Slope of the tangents from point C to point D are all now negative to the curve, which indicates that if the slopes are negative, that the graph is decreasing, until we get to this point right here where the slope is 0, and then they start becoming positive again. So when we switch from negative to positive for the derivative, what that means is we're going from decreasing to increasing, which indicates that we have a local min at that value. And for the rest of the way, like we said, if the slope of the tangent is positive, the graph continues to increase from there. And they give you kind of a quick recap of that down here, where it's increasing, where it's decreasing. This picture does a really nice job illustrating how the first derivative can give us a lot of information about the graph. And if you think back to the title of today's lesson, today is all about curve sketching. So calculus does wonders for us in the way of knowing exactly what a graph looks like just by using some calculus techniques. We can throw those graphing well, don't throw your calculator out the window yet. Okay, we still want the calculator to help us confirm things. But we have a really solid understanding of what graphs look like based on all of your years of math leading up to this, plus now what we get to add on with calculus. Okay. So here's what we're going to do in order to show extrema using the first derivative. So a point in the domain of a function f at which f prime equals 0 or f prime does not exist is called a critical point of f. So what we're going to do here is we are going to list critical points. And critical points allow us to find where we have maxes and mins. Okay. So the critical points are exactly where that definition states, where the derivative equals 0, we're going to have critical points, right? Slope of the tangent is 0, we've got a max or we've got a min. If the derivative doesn't exist, that's a critical point that we can definitely find maxes and mins around. You know, can we visualize what that would look like? How about this point right here? Okay, we're definitely continuous at this value, but would the derivative exist here? Would the slopes of the tangent lines from the left equal the slope of the tangent lines from the right? Doesn't look like that to me. It's kind of like a sharp, weird point that we're approaching, and it's definitely a max, but it would be where f prime does not exist. So we have to analyze that as well. And then the endpoints. So if we're on a closed interval, the maxes and mins, we have to check those endpoints to make sure that we don't have any absolute max or mins on the endpoints if they're not at the interior points where this is true. So to determine where a function f of x is local extrema, we can use an f prime number line. This will become pretty classic in our examples to do some curve sketching with. F prime number lines help us to justify where a function is increasing, decreasing, and where it exhibits extreme values. So here's an example of a graph that I'll have you copy into your notes. So we have this graph f of x. At this value x equals a, we have an extreme value. We also have an extreme value at x equals b. So what I'm going to show you right now is what the f prime number line looks like for f of x. So of course, you guys know at this point, if you need to hit pause to kind of keep up with the notes, we should be good at doing that. Here's what an f prime number line would look like given this graph. The extreme values, the critical points in this case, come from x equals a and x equals b. And to the left of a, we can see that the slopes of the tangent lines are negative. Right? Anything I would draw to the curve to the left of a is going to have a negative slope, which means that the original graph of f of x is decreasing. Then when I go in between a and b, what we can see is that now the slopes of the tangent lines are positive. And since all the slopes of the tangent lines there are positive, we know that the graph is increasing from a to b. And then finally, once I reach point b, now we switch back over to negative slopes. So when the slopes of the tangents are negative, we get that the graph returns to decreasing. So beyond even talking about where things are increasing and decreasing here, we can talk, of course, about the extrema that are located at points A and B. When we switch from negative over to positive, from decreasing over to increasing, we know that that's going to represent a local min on the graph. So that's what I have first here. There's a local min at x equals a. And here's the justification as to why. And this is going to be really important. I know it seems like a lot of words to write, but you can't just say there's a min at x equals a based on the f prime number line. You have to describe what the number line is telling you. So since f prime of a equals 0, right, the slope of the tangent at a is 0, and the derivative is negative, less than 0 to the left, and greater than 0 to the right of a, that's the justification as to why we have a local min at x equals a. So if it's negative to the left and it's positive on the right, to go from negative to positive, decreasing to increasing means we've got a local min. And then we can use a really similar justification to justify why at x equals b, we have a local max. So there's a local max at x equals b since f prime of b equals 0. And the derivative goes from positive to negative, right? Positive to the left, and it's negative less than 0 to the right of b. That's the justification that you need to write to show that there's a local max there. And yes, I need to see these words, okay? Don't shortchange me on your justification there. There are other ways of justifying that we'll get into in the next few days, but for now, when you're justifying local extrema, you need to write out these statements using your f prime number line. And then, of course, we can see where it's increasing and decreasing according to the f prime number line. It's increasing over the interval from a to b, where the slopes of the tangents were positive, decreasing over these two intervals here. All right. So I know you've kind of done a lot of copying up until this point. I think we're at the point where we're now ready to take everything that we know and kind of put it all together into sketching a curve with a really solid amount of accuracy without even touching the calculator. We're going to use techniques that we just talked about here that are calculus-based techniques, and we're also going to talk about other things we can identify that would help me in sketching an accurate graph. So on the next page, curve sketching. Here's what we're going to sketch. X to the third minus 3/2 x squared. We're going to determine intervals where the graph is increasing and decreasing, the coordinates of the extrema, and then we'll sketch a graph based on that. Now, it's nice to know some other information other than increasing, decreasing, and extrema. There are other key points that you'd probably want to sketch when making a complete graph of f of x up here. And that's what this first question is all about here, actually. How would you approach this before calculus? So like maybe pre-calculus. Right? All right, so before this in pre-calc honors last year, what would you be doing? You would be talking about maybe where this thing crosses the x and the y axes. So if we talk about x-intercepts of the roots, you would set the equation x cubed minus 3/2 x squared equal to 0. And if you factor out an x squared to get x minus 3/2 left over, we get that we have roots at x equals 0 and then x equals positive 3/2. Now that x equals 0, by the way, we should probably indicate somehow that because it's x squared equal to 0 that we're solving there, x equals 0 is a double root. So we know we have 3 roots total according to the fundamental theorem of algebra that says the degree of the polynomial equals the number of roots. So we do have 3 real roots, which is kind of nice, a double root at 0, and then a single root x equals positive 3/2. We can talk about y-intercepts, right? And the y-intercept is actually going to be 0, 0 in this example because we have that root at x equals 0. And the last thing you can probably get without necessarily touching the calculator is maybe just a quick reminder of what the end behavior looks like for this cubic polynomial. So for cubic polynomials with a positive leading coefficient, we would get end behavior that the tails look like this, right? As x goes to infinity, y goes to infinity. And then as x goes to negative infinity, y should also go to negative infinity. So we have some good solid info here before we even got to calculus this year. But what I don't know is, where this graph is going to exhibit some of its local max and min values. I wouldn't necessarily know that without looking at the calculator in pre-calculus. But now, using calculus, we can find the derivative and then justify where we have some extrema, and then also talk about where it's increasing and decreasing. Okay, so let's go ahead and take a look at what that would look like. The derivative f prime of x, really simply using the power rule, it's going to be 3x squared minus 2 times 3/2 is 3x there. Okay, so to get the critical values, the critical points to figure out where we're going to partition around, we're going to set this equal to 0. And in this case, you can factor out a quick GCF of 3x. That leaves you with x minus 1. So the critical points that you have to put on your f prime number line are x equals 0 and x equals 1. So we've got an f prime number line over here. We've got 0, we've got 1. And if you test in each of these regions, we know that for x equals 0 to the left of that, like negative 1, this would be negative and this would be negative, and negative times negative is positive. In between 0 and 1, like 0.5, it would be positive times negative, so that's negative. And to the right of 1, you would get positive times positive. So right away, what I kind of like to do here is I write that I know I'm increasing, where the derivative is positive, right? Slopes of the tangent lines are positive. The graph of f is increasing. Then we switch over to decreasing and back to increasing again. And if we think about what this starts to look like then, as we go from an increasing graph to a decreasing graph, we're definitely going to have a local max at x equals 0. And as we switch from decreasing over to increasing, it's going to represent a local min at x equals 1. So even though we can think of that logically based on our f prime number line, it does say to justify where f of x exhibits the extrema. So the justification is going to look something like this. we know we have a local max at x equals 0. Why do we know we have a local max at x equals 0? Well, since, first of all, f prime of 0 equals 0. Right, when I plug 0 into the derivative, we know that we get 0. And f prime of 0 is positive to the left, greater than 0. To the left, and negative, less than 0. To the right of 0. X equals 0 is a local max. So the justification, I know that we don't love writing out as many words as I've just written here, but it has to be something to this standard. Okay, we can't shortchange justifying and explaining. This is what the AP expectation is. If it says justify extrema, you have to write this explanation that accompanies what we saw on the f prime number line here. All right, so let's talk about then what's going on at x equals 1. We know that there's a local min at x equals 1. I bet if you hit pause right now, you could probably repeat a very similar statement to what we just wrote up there to justify the local min at x equals 1. So if you want to challenge yourself, go for it. But otherwise, I'm going to write down real quickly, since f prime of 1 is 0, and f prime of 0, or f prime of is less than 0, sorry. It's negative to the right of 1. Okay, less than 0 to the left of 1. Like I said, that reversed a second ago. And then f prime is positive to the right of 1. We have a local min at x equals 1. Okay. So those are the justifications that are needed there. And now we're like 2 seconds away from putting all this together on a graph. I know this grid has been so tempting to just jump right into. But the last thing I want to do is figure out, okay, if this is where the local max is and this is where the local min is, what are the corresponding y values that go with those? So we have to plug in these values to the original function. And f of 0 happens to be 0 in the original function up here, which kind of makes sense because we know that when something has a double root, that's going to be, in this case, an example of where a local max occurs. And then where's the local min? If you plug in 1 to the function, 1 cubed minus 3/2 times 1 squared. So that's 1 minus 3/2, which is negative 1/2. So the coordinates of the local min are 0, 0, or local max, sorry. Coordinates of the local min are at 1, comma, negative 1/2. So kind of putting all of this together. Okay, drawing a quick set of axes there. Just because we don't need a ton of space here and to really make this look nice, I'm going to space out and make every 2 spaces on the x and y axes a unit here. So there we go. Okay. So what we know is that we had roots at 0 and then 3/2. So we got 0, we've got 3/2. Those are where the x-intercepts are. We know the y-intercept also matches where the origin is there. We know that 0, 0 is also where there's a local max. So the only other point that we can plot is the local min at 1, comma, negative 1/2, right there. And then aside from that, if you were to follow what we said for end behavior, right, that we know that this graph has to be increasing to decreasing to increasing, the graph should look something like this. And we can get just that much more accurate with this local min right here at 1, comma, negative 1/2, right? Because otherwise what we've done in the past is probably bounce off of that root, come down, I don't know how far, and then just turn around and eventually go through the other root. We can get a little bit more accuracy in terms of the sketch of this curve by adding in just that extra calculus element to it all. Okay, so we're using all of our knowledge of pre-calc, roots, intercepts, and behavior, and combining it with this idea of increasing, decreasing, and being able to now determine algebraically where we have extrema. I think that probably leaves us in a good place for today. There is one more curve sketching practice that you can give a shot to. It's the same idea as before. We're going to use all the same critical info. Find your critical points. Once you find the derivative, set that to 0. One quick note of caution here is if you're going to try this one on your own, this one will have examples, critical points you have to partition around as to where the derivative does not exist. Remember that was one of our criteria for critical points. It's where the derivative equals 0 and where the derivative is dne. So think about that. All right. But otherwise, if you don't wind up getting time to finish this sketch here, or you're nervous that you're not doing it correctly, we will go over this next time I see you in class. All right. That's it for curve sketching. We'll catch you next time.